true, by the way. What I want from you is to understand how to approach this kind of questions. It's not necessary for you to copy the answers, but to understand how to approach this class of questions or this class of problems. Here, the question one says, using a suitable mathematical expression, describe the exponential and logistic sigmoidal microbial growth. Remember that in the class we said that the exponential assume that the exponential growth applies during a log phase, and that assume that growth proceeds indefinitely. That is, it does not account for the deceleration of stationary phase. And that expression, just like the name implies, states that cells will grow using an exponential trajectory. And the equation that best illustrates that exponential growth is the one here. And in your response, you have to support your response by stating that this growth was a question here. I wanted to first understand the concept, okay? Recording is not really very important, but understand the concept. That's the key things, how we should have computed it. What you should have stated in the first question A here was that when the resources are unlimited, when the cell have enough resources, they will exhibit this kind of exponential growth, in which case xt, which is the cell concentration at any time, will be equal to the inoculum size, exponential, the specific growth rate mu, and the time t. Is an exponential equation of growth, which assume that cells will grow indefinitely. And that is only possible when cells are in the presence of unlimited supply of nutrient. Okay? And they said you should also state the equation for the sigmoidal microbial growth model or the logistic growth model. Of course, the logistic growth model takes into account the fact that nutrient will be exhausted, that cells will enter the deceleration and stationary phase. And what you should have done while stating the equation would be to write in your document that when resources are limited, cells exhibit the logistic growth, right? Not unlike the exponential growth. When resources are limited, cells will exhibit the logistic growth. And the logistic growth, the growth rate will decrease as the resources become scarce. That is, when there is a depletion of resources. And eventually, it levels off when the nutrients are depleted to the carrying capacity is reached. And that shows a kind of S-curve with the deceleration and the stationary phase. And the logistic model that you can use to further illustrate that is the one here, okay? I'll use the logistic model here to illustrate that when resources are limited, which is a typical case, cells cannot grow exponentially, they cannot grow indefinitely, or they have to enter a decrease and a stationary phase. And that's expressed by the mathematical equation here. Now, to summarize, you are meant to use first the exponential growth equation and explain. Secondly, what you needed to do was to not talk about the logistic growth and explain using this equation to support. If you don't proceed that way, you're not going to have the mark, or maybe not the full mark. Okay? That's how you should have addressed those aspects, those two aspects. The next thing that question that was provided to you was describe 5 key requirements of a suitable sensor for bioprocess monitoring, okay? The idea is to describe. They didn't say list, they said describe. That is, in addition to you mentioning this point, you have to write a small narrative to explain how they are useful for that purpose. Okay? What I expected from you was to write. What I expected from you was to write a narrative around those key points. And you are talking about accuracy. That is, the sensor to be suitable for the reactor has to be an accurate sensor. You wrote about the importance of accuracy. A sensor that's not accurate implies that the data provided to the control unit are false, right? And consequently, in a feedback control system, a false action will be undertaken. Okay? You have to talk about suitable sensors, how to produce data that are reproducible. That is, it doesn't have to measure a particular parameter and give you a value. When you want to repeat it, it gives you a different value. This is extremely important. It has to be heat and pressure resistant. That is, the sensor has to be able to withstand autoclaving or temperature sterilization. Right? Talk about how mechanically robust a sensor has to be, right? It has to restore the rugged environment of the reactors being used. Bacteria should not adhere to those sensors. Okay, it has to be resistant to bacteria adhesion. The sensor should be stable over a long period of time. That is, the sensor itself should not be subjected to some drift. Okay, it has to be stable over a long period of time without being subjected to drift. It has to provide quick information, fast. You have to measure and information is obtained in millisecond or in second. It doesn't have to be the kind of sensor that measures and rather provide information after 1 hour. That's why we say you have to fast dynamics in relation to the measured variable. Now, the linear characteristics are majorly found on the, well, in large number of sensors, including the temperature sensors, but when you take a case of the pH sensors, most of the time it doesn't show the linear characteristics. Okay, I would like to go and read on the linear characteristics of a sensor. Take an example I've given to you that the pH sensors lack, most of them do not show linear characteristics. Now, the second question was for you to, says using a suitable diagram, describe PID control loop for temperatures in a reactor. Okay, that is, here again, you have to have the diagram. It could be any of the diagram. I repeat, any of the diagram that we encountered during the lecture. But these three parameters, PID, have to reflect on that. Then you explain as follows. You have to explain the diagram that a control feedback loop, the controller signals, you replace the value here. Sorry, the question talks about the temperature, okay? Talk about the temperature. Now here where you have a control loop described in your book, that is on the pH control loop. That is, you have to change the pH value here by the temperature, In other words, the controller output the temperature sensors, the measured temperature variable, and the final control element, the control signals. These are the key elements that are involved in the reactor. These key elements have to be present in your diagram, right? Your diagram has to show the core elements involved in that control loop, which will be the output signal, the control output signals, the temperature sensors, the measured temperature variable, the final control element, the control signals, and the temperature disturbance. Now, beside the elements, you have to explain how it works. Okay, you have to explain how it works. You said that the measure temperature process variable is subtracted from the set point value and an error is determined. The action of the controller will be based on the difference between the measured value and the set point value. In this case, the controller output will be to open or close, let's say, a cooling solutions or a water flow, a water valve, or the flow pump, or the final control element. Such a way that if the set point value, the difference between the set point value and the measured process variable is high, the controller knows whether to heat the system, right? It decides whether to heat the system or cool the system, depending on how it's configured. But if the value is lesser than 0, the system will decide whether to open the valve for cooling or heating, depending on the value or depends on the configuration. Open valve for cooling or heating, depending on the configuration of the system. Okay, this is what is supposed to explain with the process control loop provided to you. Okay, as skip question 3 clearly describe the setup of a continuous system and what are the limitations because we cover in the class extensively. That's why I skipped that question. The next one was the early stage of process development, experiment carried out in the continuous reactors operated in a series of dilution rate by a constant serial feed stream, pH, aeration, and temperature. The feed had a limiting substrate concentration of 1500 milligram per liter, and the reactor had a working volume of 10 liters. Steady state process data are shown in the table below. The idea is for you to have a look at this set of data. You have the feed flow rate, you have the substrate concentration corresponding to each of the flow rate, and you have the cell biomass corresponding to each of the flow rate. The question presented to you was to find the Ks value, kinetic constant, as well as the maximum specific growth rate in this system. Okay. We will want to go to plot. We remember quite all right this. Let me just put to the screen a little bit for us to be on the same page. Okay, let me stop sharing.